Hello, today we'll take a detailed and visual look at how an ordinary tree is transformed into a sheet of paper. We'll cover the entire journey from the logging site to the paper-making machine, explaining the key chemical and mechanical processes, and also touching on environmental issues and recycling. This information will help you understand what paper is actually made of, why it comes in such different forms, and how modern technologies minimize its environmental impact. Paper is one of those familiar materials without which it's hard to imagine modern life. It surrounds us everywhere, from food packaging and books to banknotes and napkins. But have you ever wondered how a hard tree, whose trunk is barely sawn, is transformed into a thin, smooth, and sometimes incredibly strong sheet on which you can print, draw, or even build? This process isn't magic, but the result of centuries of technological evolution and complex industrial production. Today, papermaking is a highly automated assembly line where chemistry, mechanics, and precise calculations work hand in hand. In this article, we'll follow the entire process step by step, from selecting a tree in the forest to the massive papermaking machines that produce paper webs at express speed. We'll explore how cellulose, the primary fiber, is extracted from wood, why paper comes in varying strengths and whitenesses, and how the modern industry is addressing important environmental issues. Understanding this process not only satisfies curiosity, but also helps us to take a more conscious approach to consuming and recycling one of the main materials of civilization. The papermaking process begins long before the factory floor, in the forest. Not all wood is equally suitable for papermaking. The choice of wood species depends on the length and quality of the fibers, which will later become the basis of the paper sheet. Coniferous and deciduous woods are the most important in the global paper industry, and they are often combined to produce paper with specific properties. Coniferous trees such as spruce, pine, fir, and larch are prized for their long, averaging 3 to 4 millimeters, and strong fibers. These fibers, intertwined during the production process, form a dense, tear-resistant mesh. Therefore, softwood pulp serves as the basis for the production of durable papers, such as packaging cardboard and sack paper, and is also added to the furnish of book, magazine, and offset paper to increase its strength. Hardwoods, primarily birch, aspen, maple, and eucalyptus, the latter is widely cultivated in tropical and subtropical regions specifically for the pulp and paper industry, have shorter, around 1 millimeter, and finer fibers. Paper made from these fibers is smoother, denser, and more opaque. These properties are ideal for printed products where surface uniformity and print quality are critical, such as offset paper, office paper, and coated grades. Modern papermakers often use a blend of softwood and hardwood fibers to achieve a balance between strength, smoothness, and cost-effectiveness. Natural forests aren't the only source of wood. Purpose-built forest plantations with fast-growing species, such as eucalyptus or pine, are increasingly playing a role, ensuring the sustainability of the raw material. Furthermore, pulpwood, small-diameter, small-sized trunks, is also widely used in production, as well as wood processing waste such as slabs, trimmings, and sawmill chips. This makes the process more sustainable. A key alternative fiber source is waste paper. Recycling paper significantly reduces the consumption of virgin wood, water, and energy, although the fiber loses some quality with each processing cycle. Modern mills often operate using a hybrid model, using both fresh pulp and recycled paper. The choice of raw material also directly impacts the manufacturing process and its economics. Long softwood fibers require more energy to grind but produce a durable product. Short hardwood fibers are easier to process and produce a smooth finish, but may require more binders to maintain strength. Paper manufacturers constantly research and optimize raw material blends, striving to balance finished product quality, production costs, and environmental impact. In some cases, less traditional plant fiber sources such as bamboo, cotton for banknotes and high-quality documents, flax or hemp may be used to create specialized paper grades. Their use is typically limited to niche, high-end segments due to the high cost of raw materials. Thus, the first and fundamental step in creating a sheet of paper is not simply harvesting wood, but a complex strategic selection and preparation of the right raw material, the characteristics of which directly impact the properties, cost, and environmental footprint of the future product. Without understanding this stage, it is impossible to imagine the entire subsequent chain of transformation from wood to paper. After logging equipment delivers the tree trunks, delimbed trunks, to the pulp and paper mill, intensive mechanical preparation begins. The goal of this stage is to transform large, heterogeneous logs into standardized raw material suitable for effective chemical or mechanical debonding. The first and mandatory step is debarking, or bark removal. Bark is unsuitable for the production of high-quality pulp, as it contains few useful fibers and many mineral impurities, sand, dirt, and substances such as tannins, which can interfere with chemical processes and degrade the color of the final product. Debarking is performed in two main ways. In the mechanical method, the logs continuously rotate in a large drum, the debarking drum, where they rub against each other under the force of friction and impact, causing the bark to break off. A more modern and effective method is hydraulic debarking, which uses powerful jets of water under high pressure to remove the bark, minimizing the loss of valuable wood and allowing for a better surface cleanliness. The debarked logs are then sent to a washing station to remove any remaining sand, dirt, and small bark particles. The next step is the production of process chips. Debarked logs are fed into a chipper crusher, the main working element of which is a massive rotor with several steel knives. Rotating at high speed, the knives chop the wood into small pieces of a specified size, typically 15 to 30 millimeters long and a few millimeters thick. The size and uniformity of the chips are critical for subsequent processes. Chips that are too large will not be properly and uniformly impregnated with chemical reagents during pulping, while chips that are too small will create excessive flow resistance in the digester and can lead to a decrease in fiber quality. After chopping, the chips pass through a system of screens where they are sorted. The optimally sized fraction is sent to storage silos for further use. Small chips, fines, and sawdust are often burned in the plant's boilers to generate energy, while larger chips are returned for regrinding. The prepared and sorted chips are no longer logs, but a free-flowing homogeneous mass, ready for the main transformation, the separation of cellulose fibers during the pulping process. This mechanical preparation stage, despite its apparent simplicity, is the foundation for all subsequent production, as the uniformity and efficiency of chemical reactions, pulp yield, and ultimately, the properties of the paper directly depend on the quality of the chips. Once the wood chips are homogeneous, the key and most complex stage begins, separating the cellulose fibers from the wood by breaking down the natural glue that holds them together. This glue is lignin, a complex polymer compound that gives wood its rigidity and resistance to decay. Two fundamentally different methods are used to separate the fibers, mechanical and chemical, yielding products with different properties and costs. The mechanical method is the most direct but also the most crude. The wood chips are literally ground on rotating stones or between grinder discs under high pressure and steam, thermomechanical pulping, TMP, or with a slight chemical treatment, chemothermomechanical pulping, CTMP. As a result, the wood is separated into individual fibers and fiber bundles. The main advantage of this method is a very high yield, up to 95% of the wood mass, since lignin is practically not removed. However, it is also the main disadvantage. Lignin remaining in the pulp oxidizes over time under the influence of light and air, causing yellowing and brittleness of the paper. Therefore, mechanical pulping is used primarily for the production of inexpensive products not intended for long-term storage, newsprint, corrugated cardboard base, and low-grade packaging. The chemical method is a complex multi-stage process aimed at the selective dissolution and removal of lignin with minimal damage to the cellulose fibers. It yields a lower final product, approximately 40–50%, but produces high-quality, strong, and light-colored fiber. The dominant technology worldwide is the sulfate kraft process. Chips are cooked in sealed metal digesters at high temperature, up to 170 degrees, and pressure in a solution containing sodium hydroxide, NaOH, and sodium sulfide, Na2S, the so-called white liquor. Under these conditions, the lignin breaks down and dissolves, leaving the cellulose behind. The resulting mass has a dark brown color due to the presence of residual lignin and its degradation products. It is then washed several times, separating it from the spent black liquor, which is then evaporated and burned to recover chemicals and generate energy. The outdated sulfite process, where pulping is carried out in a solution of sulfurous acid salts, produces lighter but less durable pulp and is associated with greater environmental problems. The next critical step is bleaching. Brown unbleached kraft pulp is suitable only for the production of packaging materials, e.g. cement bags. To produce white paper, the pulp must be bleached, which means removing residual lignin and color compounds. Modern bleaching is a multi-stage process using a series of oxidizing agents. Traditional chlorine-containing methods are practically no longer used due to their environmental hazards. Instead, ECF, chlorine dioxide bleaching, and TCF, chlorine-free bleaching technologies are used, using oxygen, O2, ozone, RO3, and hydrogen peroxide, NH2O2. These methods produce high-brightness pulp while minimizing the formation of toxic, persistent organic compounds. After bleaching, washing, and cleaning from foreign matter, sand, uncooked wood chips, we obtain clean pulp ready for further processing, the basis for paper making. This is no longer wood, but a loose, moist, fibrous mass in which individual cellulose fibers are ready to form a new leaf. The pulp obtained after cooking and bleaching is not yet finished paper, but merely its base. To transform this pulp into a product with specific properties, it must be carefully prepared. This process begins with beating or refining. Fresh cellulose fibers are stiff and poorly bonded. To change their structure, the pulp is passed through specialized machines called refiners, where rotating discs with notches subject the fibers to mechanical stress. As a result, the fibers are not torn but crushed and combed, their surface becoming covered with tiny fibers called fibrils. This is critical. Later, during sheet formation and drying, these fibrils intertwine and form millions of hydrogen bonds, which give the paper its mechanical strength. The degree of beating is an adjustable parameter. High refining produces a denser, smoother, and more opaque paper, but can reduce its tensile strength. Light refining preserves the length of the fibers and creates a looser, more porous, and stronger structure suitable for packaging materials. Parallel to or immediately after milling, a whole range of chemical additives are added to the pulp, each performing a specific function. To improve printing properties and appearance, fillers, finely ground minerals such as kaolin, white clay, calcium carbonate, chalk, or titanium dioxide are added. These particles fill the voids between the fibers, making the paper smoother, denser, more opaque, and whiter. They also reduce costs by saving on more expensive cellulose fiber. The next essential group of additives are sizing agents. Pure cellulose is hydrophilic, meaning it readily absorbs water, which would otherwise make writing with ink or printing impossible. To make the paper moisture-resistant, it is sized. Historically, rosin was used for this purpose. Today, synthetic adhesives such as alkyl ketene dimer, AKD, are more commonly used. Sizing can be accomplished by adding a substance directly to the pulp, bulk sizing, or by applying it to the nearly finished sheet, surface sizing. Dyes are used to correct color, and optical brighteners are used to achieve a bright, dazzling white effect. These are special fluorescent substances that convert invisible ultraviolet radiation into visible blue light, visually neutralizing yellowish tones. Depending on the final use of the paper, other additives may be included in the composition to improve moisture resistance, for example, melamine formaldehyde resins, to impart fire resistance, or to protect against microorganisms. After all components have been added and thoroughly mixed, the pulp is heavily diluted with water. At this stage, it is a very fluid suspension, consisting of 99.5% water and only 0.5% solid fiber particles and additives. This dilution is necessary for the next step. Only in this form can the pulp be evenly distributed on the paper machine wire to form an endless web. Thus, the pulp preparation stage is a fine-tuning of the formula, where mechanical fiber processing is combined with precise chemical dosing to produce not just a sheet of pressed fibers, but a complex composite material with predetermined and controlled properties of strength, whiteness, smoothness, and durability. Prepared and diluted with water to a liquid suspension, the paper pulp enters the head of a gigantic paper machine, a complex machine up to 150 meters long. This is where the magical transformation of the liquid suspension into a dense, continuous, and dry paper web occurs. The first section of the machine is the wire section. The pulp, with a concentration of approximately 0.51%, is fed under pressure onto an endlessly moving wire made of synthetic materials or metal alloys. The key function of this section is to evenly distribute the fibers and begin removing excess water. Under the influence of gravity, water begins to flow freely through the mesh openings, a process called gravity dewatering. To accelerate this process and ensure a more uniform fiber distribution, the wire is vibrated from side to side. Next, suction boxes come into play, creating a vacuum under the wire and literally drawing another portion of water from the forming web. By the end of the mesh section, a loose, wet water content of about 80% endless web is formed from the liquid suspension, which already has sufficient strength to be transferred to the next section without breaking. But that's not all that happens on the wire. This is where the direction of most fibers is determined. They tend to align with the direction of the wire. This creates the so-called machine direction in the paper, in which the sheet is stronger and more tear-resistant than in the cross direction. For some special types of paper that require equal strength in all directions, more complex pulp feed systems are used, such as those using two wires, twin wire, which form the web by compressing the pulp on both sides, which also reduces the double-sidedness, the difference in properties between the top and bottom sides of the sheet. The next stage is the pressing section. The wet paper web, now without the support mesh, passes through several pairs of powerful rollers covered with felt or polymer materials. These presses apply high mechanical pressure to the web, squeezing out up to 60% of the remaining water. This process not only dehydrates the paper, but also compacts its structure, bringing the fibers closer together and increasing their contact area, which will subsequently lead to the formation of stronger hydrogen bonds during drying. Press designs are constantly being improved. Modern shoe or roller presses allow for a gradual increase in pressure, preventing crushing of the still fragile web structure and ensuring more uniform compaction. After the pressing section, the paper web becomes much denser and stronger, but still contains approximately 40 and 50% moisture. At this stage, surface sizing can also be performed, where special compounds are applied to the half-ton to impart specific properties. The final stage of dewatering occurs in the drying section of the machine. Here, the paper web snakes through multiple 40 to 80 massive steel cylinders within which superheated steam circulates. The cylinder surfaces are heated to a temperature of 100 to 130 degrees Celsius. Upon contact, any remaining water in the paper rapidly evaporates. To prevent warping and ensure uniform drying, the paper is pressed tightly against the cylinder surface using felt belts. The drying process is strictly controlled, as too rapid evaporation can cause brittleness, while too slow evaporation can reduce productivity. Heat is distributed among the sections, allowing precise control of the drying profile. By the end of the drying section, the paper's moisture content drops to an optimal 47%. It is at this stage, as the last layers of water are removed, that strong hydrogen bonds are finally formed between the fibers, which have been brought together and activated during the milling process, giving the dry paper its mechanical properties. After exiting the drying section, the paper may pass through finishing equipment. Most often, this is a calender, a stack of 5-10 vertically arranged polished rollers between which the paper web is passed under pressure. This process, called calendering, further compacts the paper, making its surface smoother and glossier and its thickness uniform. The intensity of calendering is adjusted depending on the required paper type. Heavy calendering produces coated glossy paper, while light calendering produces a loose matte finish, such as for watercolors. For special grades, embossing or textured calenders may be used, which leave a pattern on the paper surface. At the very end of this production line, the finished paper web is wound onto a huge rotating core, forming a roll, paper web, up to 10 meters wide and weighing several tens of tons. The winding must be uniform and under a certain tension to prevent deformation and wrinkles. This roll, or web, is the final product of the paper machine and is sent for further rewinding, slitting, cross-cutting, packaging, or as the base for additional coatings during the coated paper production process. The entire process, from the screen to the roll, occurs at speeds reaching 100 to 120 km/h, requiring the highest precision in synchronizing all machine components. And now we know that the journey from tree to paper is an impressive example of transforming natural raw materials into high-tech products. The process involves carefully selecting wood, mechanically processing it into chips, complex chemical or mechanical separation of cellulose fibers, and multi-stage cleaning and bleaching. Then the prepared pulp, enriched with additives for strength, whiteness, and smoothness, passes through a giant paper-making machine where it is formed, dewatered, pressed, dried, and finished into a continuous web. Modern paper production is a balance between quality, efficiency, and environmental responsibility. Understanding this multi-stage process allows us to appreciate not only the material itself, but also the complex labor, science, and engineering behind each sheet. It also highlights the importance of responsible consumption and recycling of paper to preserve our planet's resources.
That's all for today's video. Don't forget to like and subscribe to the channel so you don't miss any videos. See you soon.